Kinetics. Kinetics is the study of reaction rates. Where have you seen a rate in real life? Maybe you see it on your way into school.
When you're driving and it has like the RPM.
Okay. Yes, the RPMs on your speedometer and stuff, or the tachometer, that's certainly a rate. I was actually more looking for speed limit signs, but both of those are great examples. All right, so you see rates all the time. Rate is the change, well, for speed limit, it's the change in distance over the change in time. So rate is the change in something over the change in time. For reactions, that change in something is going to be change in amount of your reactants or products over the change in time. We're going to be looking at how fast or slow reactions occur by looking at and measuring their change in their concentrations per time, or maybe even their change in partial pressures over time. Okay. Up until this point, most of the reactions that you've done in your careers as junior chemists have been very fast, okay? They occur almost instantaneously. We don't have to wait a real long time for reactions to occur. Right now, you are all, most of you should be doing a chemical reaction in your body because you all just came back from lunch. You're all digesting your food. It's not like as soon as you swallowed your food and your food hit your stomach and touched that acid that it immediately reacted and digested. Okay, it takes a while for all that food to break down. That's a slower reaction rate, okay, or smaller reaction rate. And depending upon the type of food you eat, it will take either longer or shorter to digest. Like those more complex carbohydrates are going to take a little bit longer. Those simple sugars, you digest them pretty quickly, which is why you get those sugar rushes. Okay. So, reaction rates. Next class, we're doing a lab where we're going to look at different ways to change the rate of reaction or change how fast or slow it occurs. But for right now, we're just going to be talking about how we can use the rate of reaction to find out other things about the reaction. So let's look at this hypothetical reaction here. 2A plus NB goes to QC plus RD, where N, Q, and R are the coefficients on B, C, and D, respectively. Okay. And then we're given some information about those substances. What are some things you notices? What are some things you notice about those reaction rates? Or those rates that are given?
The bottom two are positive and the top two.
But what do you mean? They're all positive?
No, I'm talking about the coefficient to the left.
You're talking about here?
Yeah.
Yeah, so why are these negative and these are positive?
Because those are the products, no reactants.
Well, you tell me. From the equation, which ones are our reactants? A and B, which are these, right? So A and B are negative, and C and D are positive. But why are A and B negative? Why do we have a negative sign in front of the change in concentration over the change in time for A and B? What? Why? Okay, they're reactants. What's happening to reactants over time? They're reacting and they're forming products. If I have a flask, maybe a volumetric flask, if I have a flask and I have A and B in that flask, their amounts are going to decrease over time as C and D are formed. So that's why we had to have a negative in front of reactants, because the change in concentration for reactants will always be negative, because you're always ending at a smaller number than where you started. So we then have to put a negative in front of that to keep our actual value positive. Okay? What's up with our units? Moles over liters times seconds. Well, how did we get there? Moles per liter is concentration. So this can also be written as molarity per second. You could write it as either one. But understanding how to manipulate units like that is super important for this unit. Being able to do the algebra with the units is really important. It's not going to make or break your grade, but it might be a difference of like half a letter grade or something, okay, on your test. If you cannot figure out how to manipulate units through stuff like this, you will lose points on your test, okay? And I'll show you some shortcuts, and I'll show you what I mean by where we're going to be looking at these units, okay? All right, so looking at this reaction, we're given the rates of change of concentration for all of the substances. And from the information given, we can figure out the coefficients of N, Q, and R. Okay, we know the coefficient on A, and we're going to find the coefficient on B, C, and D. So looking at reaction, or the rate for A, comparing it to the rate for B. Which one's changing at a faster rate? B, right? How much faster is B changing? What? Yes, it's changing 3 times faster. So really to go from A to B, we had to multiply by 3. So correct me if I'm wrong in this statement. B disappears 3 times as fast as A. Is that statement valid? Yes, based off of the data given, B is disappearing 3 times as fast as A is disappearing. Well, because 0.05, to get it to 0.15, you have to multiply by 3. Don't look at the coefficients. Not yet, at least. So since B is disappearing 3 times that of A, the coefficient in front of B would be 3 times that is the coefficient in front of A. So therefore, N has to be 6. We can do the same thing for both substances C and D. Let me walk you through C. So for substance C, what do we want to compare it to? Okay, let's compare it to B. That's what I did. So from B to C, what do we multiply by? 1/2. Now, I can't say that C is disappearing half as fast as B because C is not disappearing. What is it doing? It's appearing because it's a product. It's being produced. So we could say that C appears 1/2 times as fast as B disappears. And if we know the coefficient in front of B is 6, then the coefficient in front of C has to be half that. What's half of 6? 3. Yay, we can do math. Okay. So see how I'm doing that? Why don't you guys take a moment to figure out the coefficient in front of D. I'm going to pause it while you guys do that. So you should have figured out that the coefficient in front of D, or the coefficient R, is 1. Because from here to here, you could have compared it to any of them, but I compared it to C. I found that from C to D, it's 1/3. So D appears 1/3 as fast as, as C. Therefore, R has to be 1/3 of Q, which is 1. Okay? Questions? All right. That's using, those are called relative rates. There are some questions like that in your first homework. Homework 4A. Now we're going to look at another thing, which is called method of initial rates. MOIR, method of initial rates. Okay. This unit is grounded in calculus, though we won't be doing calculus with it. Okay, calculus is not a prerequisite for this course. It's not even a co-requisite. You don't need to have calculus to do AP chemistry. We will eventually be talking about what's called an integrated rate law, And I know that not all of you have done integrals yet. Don't worry, they're very fun when you get there. Eventually you'll get to the point where you get to rotate things about an axis and find the volume of a shape. It's very fun, okay? So, the derivation for those integrated rate laws is in your textbook and is in the guided notes. I will not be going through the derivation, but if you want to see the derivation, you can look in your guided notes or in the textbook, okay? What we're going to be doing right now is actually writing what's called the differential rate law, which I know, differential, it's a derivative, woo, okay? Because that's what, rates are, derivatives, okay. All right, so we're going to be we're going to be writing what's called a differential rate law, which in general for this reaction looks like this. Rate equals some rate constant k, which we will eventually solve for, and it has special units, times, what do those brackets mean? Concentration of our reactant NO2 raised to the m power times the concentration of F2 raised to the n power. Yeah, can you hit the lights? I know that green doesn't show up very well. There we go. So much better. Okay. M and N are what are called the orders of reaction for each of these substances. Okay. It's essentially how much that reactant influences the overall rate of reaction. Okay? And K is a rate constant. Rate constants are dependent on temperature and they are unique for the reaction. Okay, so if this was a different reaction, it wouldn't have the same rate constant. For this reaction, if we looked at it at 75 Celsius, its rate constant would change. We're not there yet to figure out how it changes with temperature. Okay, that's later. So we have this reaction. Now, the orders of reaction, M and N, are not necessarily the coefficients from the balanced chemical equation. Now, we know that the change in concentrations are going to be dependent on their coefficients, like what we did last time. But the rate of reaction, the actual rate that this reaction is occurring, is not dependent upon coefficients. It's dependent upon the orders of reaction of the reactants. Okay? The way we do method of initial rates is you have to have a series of experiments done with the same reaction at the same temperature, varying the concentrations of the reactants. Okay? So as you can see, we have 3 experiments, and your packet has it. My board is missing the multiplication sign in experiment 3's rate. But we have 3 experiments where we changed the concentration of NO2 and F2, and we measured how that changed that rate. Okay? Our goal is to figure out M, N, and K. For letter A, we're only going to figure out M and N. D will figure out K. This other letter will figure out this other letter. In part D, we will figure out what the rate constant is. But first, let's figure out what M and N are. We have multiple variables here. Right? So mathematically, we need to get rid of some of them. Actually, we have 3 variables. We need to get rid of 2 to solve for the third. Right? Because you can only have 1 variable that you're solving for in an equation at one time. So the only way, or the best way to do this, and the way we're going to do this with method of initial rates, is we're going to set up our differential rate law, what I wrote up here in green, with the information from an experiment, and then divide it by that same rate law with another experiment's information. So we want to find 2 experiments where only one concentration is changing and the other one stays about the same. Now, which one do we want to tackle first? Do we want to find the order for NO2 or the order for F2? It doesn't matter which one we find first. Okay, let's find the order for NO2 first. So we want to find an experiment. We want to find 2 experiments where only the concentration of NO2 is changing and F2 stays roughly the same. So which two experiments is only NO2 changing? 1 and 2. Because see how F2 is staying the same? It's roughly the same. So only NO2 is changing for those two experiments. So we're going to write out this information. Now, let's do experiment 1 over experiment 2. And I'll explain why I'm doing that in a moment. What is the rate of experiment 1? 1.90 times 10 to the negative third. And for right now, you can leave off units because they're not going to come into play until later. Orders don't have units. They're just a number. Okay? Equals some constant K, we don't know what that is, times the concentration of NO2 in experiment 1, which is 0.0482, raised to some power m, times the concentration of F2 for experiment 1, which is 0.0318, raised to some power n. And now we're going to take that entire thing and divide it by that same reaction, but now with information from experiment 2 in it. What's the rate for experiment 2? 4.69 times 10 to the negative 4 equals some rate constant K times the concentration of NO2 for this experiment, which is 0.0120 raised to the m, times 0.0315 raised to the n. We have a few things that can cancel out. K should cancel because both of these experiments are of the same reaction and they were at the same temperature. So K should be constant because that is the definition of being a rate constant. Does anything else cancel out? Yeah, this part. Because these are roughly the same, that's going to be practically 1, so therefore this goes away. So all we're left with is the rate equals this over this to the m. Okay. Now the reason I wanted to do 1 over 2 and not 2 over 1 is because I wanted to get, it's easier to work with like whole numbers than it is to work with fractional numbers. So the rate of 1 was larger than the rate of 2, so I wanted to do 1 over 2. If 2's rate was greater, I would do 2 over 1. And that's just to set me up later for easier numbers to work with. Okay? So now in your calculators, what you're going to do is you're going to solve the left side. It should be around a whole number, or like if it's not a whole number, then write down more of it. But it should be, if it's close to a whole number, make it a whole number. So when you do 1.9 times 10 to the negative 3 over 4.69 times 10 to the negative 4, you should get like 4. Should get around 4. It's like 4.05. And then when you do 0.0482 divided by 0.0120, you get 4. You're like 4.02, but it's like roughly 4. But now that's raised to the m power. Because that's like this. Because remember, when you have two things, like if you have x to the, no, I don't want to do it like that. If you have like 2 to the x over 3 to the x, that's the same as 2/3 to the x. Yeah, math, exponents. Yeah, okay. All right. So 4 raised to what power will make it 4? 1. So m is 1. But I'm not done answering the question because it asks what are the reaction order for NO2 and F2. Saying m equals 1 isn't actually answering it. You have to write first order NO2 or first order with respect to NO2 or NO2 is first order, something along those lines. Okay? You have to basically show me that you know that when m equals 1, that means it's first order. Okay, so NO2 is first order. Now we going to find the order of reaction for F2? Yes, we need to find two experiments where NO2 stays roughly the same and only F2 changes. Which two experiments am I going to look at now? 1 and 3, because notice how for 1 and 3, the concentration of NO2 is almost exactly the same. So, looking at the rates, which one's going to go on the top? 3. So I'm going to look at 3 over 1, just to make my math easier at the end. Now, if you do it the wrong way, you're just going to get fractional numbers. Like if we had done, or decimals, if we had done 2 over 1, you would have gotten like 0.25 equals 0.25 to the m. So you could still very easily see that m had to equal 1. It's just whole numbers are easier to work with. So what's the rate for reaction 3? (7.57 times 10 to the negative 3). That equals some rate constant K times the concentration of NO2 for reaction 3 is 0.0480. Now, I know that this is first order, so I could write a 1 here, or I could put an m again because I know it's going to cancel out, or at least it should because that's the goal. Times the concentration of F2, which is 0.127 to some power n, all over the rate for reaction 1 times some constant K concentration of NO2 in experiment 1, concentration of F2 in experiment 1. What will cancel? K is going to cancel. And this term, right? Those two things cancel. So you get like 3.98 equals 3.99 to the n, right? So around 4 equals 4 to the n. So therefore n equals 1. So what order is it for F2? First order. So now what first order means? What first order means is that if we were to change the concentration of, say, F2, if we were to double the concentration of F2, the rate would double. If we were to double the concentration of NO2, the rate would double. Say F2 was second order. Say we did all the math and it worked out that F2 was second order. What that would mean is if we doubled the concentration of F2, 2 squared is 4. The rate would quadruple. Okay, so it becomes an exponential change. What if we doubled, back to what they actually are, they're both first order. If I double the concentration of either of them, the rate doubles. What if I double the concentration of both? What happens to the rate? It wouldn't double, it would quadruple, because that change gets compounded. Okay? Cool. Because the overall order of reaction, which is what you have for the next part, letter B, the overall order of reaction is going to be all the individual orders added up. What's 1 plus 1? Second order overall. Okay? It is possible to have 0 order, which means that the rate of reaction is not influenced by the amount of that reactant. The reactant's still there, it's still participating, It's just its amount doesn't change what happens with the order. Okay? Or it's not with the order, with the rate. Doesn't change the rate. So it's not the same as limiting an excess reactants. It's more of once we talk about mechanisms, I'll explain to you how you can have a reactant that isn't influencing the rate. Okay. It is possible to have half order, though we're not really going to see much half order. The main ones we're going to see are first, second, and zero, kind of in that order. Most of the things we're going to look at are going to be first order. Same thing with the AP exam. Most things are going to be first order. Though we'll also see some second orders, and then occasionally zero order. Those are the big three. Okay. So the specific rate law for this reaction, it's that differential rate law again that we wrote back here in green, but now we know what M and N are. So we're just going to fill those in. So rate equals some constant K times the concentration of NO2 to the first power times the concentration of F2 to the first power. That is our specific rate law. And yes, you should write the ones. This is the one place where I ask that you write the ones. It's here. Okay? That way I know you didn't just leave it off and that you know that they're first order for both of those. Now, to figure out the rate constant, that's that K value, pick an experiment. Pick one experiment. And yes, I just made algebra a verb. Okay, plug in values and algebra it. So, doesn't matter which experiment we pick because they were all at the same temperature. Therefore, the K should be the same for all of them. There might be slight variations if you were to actually solve K for each one. There might be slight variations, but you should get around the same value. So which one do you want to pick, Anthony? 1, 2, or 3? 3. Okay. Let's look at experiment 3. If you don't like experiment 3, you can pick a different one. All right, we're going to plug in the information we have to our rate law and solve for K, because that's our only variable now. So the rate for experiment 3 is 7.5. That's supposed to be 5. 7.57 times 10 to the negative 3. I'm going to leave units off for now as well. We'll handle the units at the end. Equals some constant K times the concentration of NO2 for experiment 3, which is 0.0480, raised to the first, times 0.127, raised to the first. So now I'm just doing algebra. And what do you get for K? 1.24? Now, rate constants always need units on them. Okay, so now let's talk about the units. Let's work through the algebra of the units first, and then I'll show you a shortcut. Okay? So for the algebra, the units on our rate, remember we could write it as moles per liter second, or we could write it as molarity per second, either one. Okay? And then the units on both of these were molarity and molarity. And we raised them to the first power so our unit didn't become squared or anything like that. So we ended up doing molarity per second divided by molarity times molarity. So let's reduce that down. One of our molarities cancels, right? But our other one doesn't. So we end up with 1 over seconds over molarity, which that reduces or simplifies to what? 1 over molarity times seconds, or seconds times molarity. So that, or if you had left it as moles per liter, you would have gotten to liters over mole second. Either one. Because if molarity is moles per liter, 1 over molarity would be liters over moles. only if this was 1 over molarity here. So here, right here, this is the same as 1 over seconds times, this is just molarity.
Yes.
So inverse that is
It's dividing by molarity.
1 over molarity.
But like if this was being divided by molarity, once you flip it, so it would be.
We are dividing by molarity.
No,
It's the same thing.
I'm saying dividing by 1. Oh, okay. I see what I was confused on.
Yeah, if we were
If
we were doing
fraction over
1 over seconds over 1 over molarity, then that would be molarity over seconds. That's, because you multiply by the inverse. I'm going to erase that because that's not what it was. All right. The shortcut. The unit shortcut for K. It's based off of the overall order. Okay? Once you've figured out your overall order, you can very easily figure out the units on K. So it's going to be 1 over your time unit times your amount unit to the overall order minus 1. Oh, that's ugly. Minus 1. So 1 over your time unit times overall, or amount unit to the overall order minus 1. Not all of our time units will be seconds. You want to look at your rate to figure out what unit of time we have. Sometimes it's hours, sometimes it's minutes, days, years, millennia, whatever. Okay? Amount unit. For this problem, that's concentration. For the next one, it's partial pressure. Okay? So it's either one. So amount is going to be concentration or pressure. And I think there might be a homework problem at some point where it's like density or something like that. Okay? But some sort of, whatever we're using to describe the amount of the substance. Okay? What time are we done here?
3:55.
3:49. Okay. Okay, cool. 2:49. 49. We have about 10 minutes left, a little over 10 minutes, which is more than enough time to get through the next problem because the next problem is not as lengthy now that we've done one. Okay? Cool? All right, for the next one. This next one is much cleaner, as it even says in the problem. So we're going to do it through table logic instead. Right off the bat, something you should notice is that we have A, 4 experiments as opposed to just 3, and B, we now have partial pressure of gases as opposed to concentration. We do it the same way. The process is the same. Okay? So let's write our general rate law from rate constant K times the pressure of NO raised to some order M. Some people do like XYZ. I think the textbook does XYZ. I do MNP. I typically don't do O because then it looks like a 0 and it's confusing. You pick whatever 3, like, I think the most you'll ever have is 3 reactants. Pick whatever 3 letters you like. You could do your initials for all I care, as long as it's 3 distinct letters. So if your initials are all the same, sorry, you have to pick new letters. Okay? Times the pressure of H2 raised to the N. Okay? So, just like last time, we're going to find 2 experiments, but this one's cleaner, so we're going to do it through table logic. We're not going to do all that algebra that we did. We're not going to write everything out, divide, all that stuff. Instead, we're still going to have to find 2 experiments in which only one pressure is changing. So, which one do we want to tackle first? NO or H2? NO, all right. Which 2 experiments is only the pressure of NO changing? 3 and 4. So from 3 to 4, what is happening to the pressure of NO? It's doubling, multiplying by 2. And therefore, what's happening roughly to the initial rate? It's quadrupling. So here's what you have to write down. The minimum amount of writing that you need to do in order to receive full credit, full marks on my tests or the AP exam is in experiments 3 and 4, as PNO doubles with all else constant, rate quadruples. Or if you can't remember the word quadruples in the heat of the moment, the stress from the test, stress from the exam, you could say multiplies by 4. Okay? So therefore, what order of reaction is it for NO? Second order. Therefore, it's second order for NO. Basically, by doing this table logic, we get to that last little bit, like what we had back here, where we got 4 equals 4 to the m. That's basically where we can get to through table logic. And we can figure out, oh, it's got to be second order for this to be quadrupling. Mm-hmm.
Why does the pressure matter then if we're just looking at it quadrupling?
Because the pressure is another way. It's one way we can describe the amount of a gas. So you're doubling the amount of NO, and it's being measured through its pressure.
If it was 29, would it still be 2, or would it be 3?
Well, if we tripled and then it non-tupled, multiplied by 9, 3 raised to what power is 9? 2. Yeah, it would still be 2. It's exponents. All right, so which 2 experiments are we going to look at for H2? 1 and 2. So from experiment 1 to experiment 2, what are we doing to the H2 pressure? Doubling it. And what's happening to the initial rate? It's roughly doubling, right? So what you have to write down is in experiments 1 and 2, as the pressure of H2 doubles with all else constant. That is important. Please do not forget to state that. The rate doubles. So since one doubles, the other one doubles, what order is that? First order for H2. And second order for NO. Table logic is obviously nicer and easier and much simpler to do. It doesn't take up as much space, not as much work. Table logic will not always work, though. You will not always be able to do table logic. Sometimes doing what we did in the last one, doing the algebra, will always work. Table logic won't always be applicable. Sometimes you have to do a mix. Or sometimes you can do a mix where you do table logic to find a couple of them and then algebra to find a third. Or table logic to find one, algebra to find the other. Okay? All right, what order is it overall? 3, because we had 2 for NO and 1 for H2, so third order overall. And from that order, we can find the units on K for part D. Let's first write the specific rate law. The specific rate law, you still put K. You don't actually solve for the rate constant yet.
Even if you have this, would you still put K?
Yeah, we can just still put K. Unless it specifically asks for you to put the value of the rate constant in the formula. NO, what's NO going to be raised to? The 2. And H2 to the 1. Okay? And now to find the rate constant, we're just going to pick one of those experiments and plug and chug, right? Which experiment do you want to do? I heard 1 first time. So the rate for experiment 1 is 0.66 equals some rate constant K times the pressure for NO is 400, and that's squared, times the pressure for H2, which is 150. will be like a ginormous number. Ginormously small number. Yeah, except for we only have one sig fig. 3 times 10 to the negative 8. Now our units, you can go through the algebra figuring out the units, or you can use the shortcut, either one. There's merits to both. The shortcut's nice and easy, but understanding the algebra is so important. All right, so since the third order, so 1 over our time unit, what's our time unit? Seconds times, what was our amount unit? Pressure in millimeters of mercury. mmHg to the overall order minus 1. So, squared. And if you did it through algebra, you would have gotten to that same unit. So there's our answer. It only applies to the millimeters of mercury. So if you want to put that in parentheses, that's fine, though I will, it's understood that it only applies to millimeters of mercury, that you're not squaring the whole bottom. Time will always be to the 1 on the bottom. Okay? The next one we're definitely not getting to in the next 4 minutes. If you've read it already, for number 4, it says, this one is a nightmare. If you can do it, you can do any of them. That one you will definitely need a combination of both table logic and that ugly algebra.